Yes. All right. With that, I'm very excited to introduce my good friend Fletcher as the next speaker, who is going to be talking about more water stuff, which is super exciting. I think water and energy. Sorry, just electricity. I apologize. It was motivated by the water stuff. So it's electricity stuff based on water stuff. Anyways, I also want to give a brief thank you to Fletcher for being our photographer today, and we are grateful.
If you were curious, our lab specializes in the water energy nexus, which is water and energy. So what we talk about most of the time. So yeah, I'm Fletcher Chapin, advised by Dr. Medley Martyr, and in the WEECO lab, so again, water and energy efficiency. So that's focused our research. If you saw Daly's talk earlier, it was about the optimization of water treatment facilities, and basically that led us. Our goal when we're doing this energy optimization is often to two things: one, to minimize the cost for the treatment facility because it's a public entity and you want them to be able to treat the water at the lowest possible cost, and also make sure to protect the environment because we're environmental engineers. In this case, we focus on electricity-related emissions, which if you hear me say scope 2 emissions, just know that means like emissions from the electric grid. So some motivation. We, as Taylor was talking about, have done a lot of research in the demand side flexibility and how that can reduce infrastructure operational costs and help achieve decarbonization. A couple of statistics. Industrial consumers use 27% of the energy consumed across the United States, so it's quite a large fraction. And more, in some ways, more importantly, they're price motivated. Around 50% of costs of most industrial processes is just their energy consumption. That's true for water facilities, but also other like just manufacturing processes, for example. So that means that they're very driven by these time of use price incentives. So a lot of times they'll have, for example, in California, more expensive electricity between 6 and 9 p.m., let's say. The problem from my environmental engineering perspective is that the emissions intensity does not line up with those costs. So we've done some research looking just at like the emissions and price signals, and in summary, they're misaligned, meaning that if I were a rational, flexible customer, I am more likely to increase my emissions compared to flat operation than decrease them. And again, as environmental engineer, I argue that is bad. We don't want that. We want people to be price incentivized to decrease their emissions. So that's the question, like, how do we understand these complex price signals and emission signals? For a little bit of background, I spent a lot of time thinking about the electric grid, but from the point of view of a consumer. So very different than an electrical engineer. This is more like, how does this electricity tariff work? And that's a lot more complicated than you might think. So there's a demand charge, which is your peak consumption during the month usually, or maybe during a certain time period of the month. Like you might have a peak demand charge from 6 to 9 and all day demand charge for any of the 24 hours. You'll have an energy charge for dollars per kilowatt hour. It also varies in time perhaps. And then you'll have a flat meter customer charge. And then, yeah, both of them could vary monthly and seasonally. And then there's an added wrinkle, which I didn't appreciate when I saw this because I didn't know what contract optimization was. You have these things called charge tiers, which on the x-axis is the optimization variable of energy consumption. What that means is if you have a charge tier, the cost function is inherently non-convex because how do I know how much I'm going to consume given time before I've solved the optimization problem for how much I'm going to consume? So that sort of these complexities, initially we just wanted to know the price of electricity at a wastewater treatment plant. That led to developing an entire package on just how do you calculate the price of electricity for any consumer because it was a lot more complicated than we anticipated. So that leads us to the software architecture. You have a package called EECO, which I now realize I don't know if I wrote out the entire acronym down there, Electric Emissions and Cost Optimizer. So the goal is threefold. One is to just calculate an electricity bill of a customer. Two is to calculate scope 2 emissions. And three is to incorporate flexibility metrics, such as like round trip efficiency. So you can sort of think of that as turning any industrial facility into a virtual battery. So if you were able to measure for your facility, like what's the power capacity, energy capacity, and round trip efficiency, which we have a whole paper on that as well that Akshay, who I don't think is here anymore, led. And so basically that's how you can model these systems. And the goal is you come with your own model. So we're not doing anything with the optimization model. You come up with whatever constraints you want, whatever, dynamics of your system. And we're going to produce an objective function of costs and emissions based on what, input signals you give. There are two helper functions, or helper packages, I guess, that help do this. One handles the unit conversions. So there's imperial units and metric units are commonly mixed in the United States electricity system. And it can be very annoying to try to figure out what the price is if you don't get the units right. And also, I guess maybe this is blasphemous at a CVXPY workshop. One of the big motivations of this is that it is agnostic to the optimization framework, meaning you can get an objective function for either Pyoma or CVXPY. That's very useful to us because we solve some of the models in our lab with Pyoma, some of CVXPY. This allows us to do the same costing package for either one. I didn't go into those details, but if anyone's curious, I'm happy to talk after about how under the hood I'm implementing functions that work with both. There's an accompanying electricity tariff data set. So this is one of the things that I would like you all to take away, basically. If you're interested in optimizing your own system, not only do we provide a way to calculate the objective function, we provide over 1,000 electricity tariffs from across the United States. So you can go download this file format and just plug it in and get an objective function basically out that helps you minimize the cost. And for anyone in the US, so you can do something like sensitivity analysis around the country to look at how different markets your system might work in different markets. That was a motivator to the initial development of this package. Again, I'm happy to talk more about this, but it's not the most interesting, so I'll continue. And this brings the demonstration. So how do you actually use this package? If I have a model and I want to go calculate costs, first, this is without any optimization. So just you have a historical load profile, you want to compute a baseline electricity bill. Again, we have a tutorial online, so if you really want to get to know the package, I would suggest you check that out. But, without reading through all the lines of code, I think I want to emphasize that you can calculate electricity bill with only, around 25 lines of code, which before this package would take quite a few more than that to go through all the different charges, compute everything. What to highlight here? So you see here, basically, I just have a CSV file that's a tariff. So that was one of the tariffs from that data set that we compiled. And then you get a charge dictionary. And so this converts the CSV tariff file to a NumPy or dictionary of NumPys arrays, basically. So it has all over the time period you asked for what's the charge at each time step. And it could have, dozens of different charges in this dictionary. And then this calculate itemized cost. This is where, when I was saying it is agnostic to the framework, if you're using Pyoma, you pass in a Pyoma model you get back a Pyoma model and you pass in a Pyoma model. That's why I'm ignoring the second output there. Is for CVXPY, there is no model object. So you just ignore that second argument and you just get a CVXPY variable back. So if I were to pass in a Pyoma model, I would get a Pyoma variable and then a Pyoma model. CVXPY, you just get the CVXPY variable. This is actually NumPy. So in this case, it's just a NumPy array, but I believe a single number because total costs. There's a calculate cost if you want just the objective. Calculate itemized cost gives you a dictionary of all the charges. So if you want more of a breakdown, so that's what I've done here. And then if you add together these two costs, you get $17,000. The reason I didn't just calculate cost is the customer charge would have been included, and this is only 2 days of an electricity bill. you don't really want to look at, because a customer charges a monthly charge. It'd be weird to add a monthly charge to 2 days worth of the bill. Another detail here, the demand scale factor, I set to 2 out of 30, because it's 2 days. So because the demand charge is the whole month, if you're doing less than a month, I would suggest scaling them so that they're proportional. Typically, whenever like the output of the problem, that's useful for like a moving horizon. Usually you run the moving horizon for a whole month, because it doesn't make sense to look at the electricity bill on a sub-monthly or sub-billing period scale. But anyway, that's, I guess, everything to understand about this. I'll quickly run through now how you optimize. First, we have a very simple battery optimization model just for this tutorial. You can see the code on GitHub if you'd like in the package. As Daly mentioned, the primary goal of this package originally was for water flexible operation. So a flexible operation of water treatment systems, where we'd have, in addition to a battery, you might have storage tanks that you can operate flexibly. But the way you use this EECO package is the same. We just provide different constraints, a different optimization model, but we have the same exact objective function. And what that would look like here, first of all, it's not shown here, but imagine that grid demand KW is just a CVXPY optimization variable. So I used to that is CP variable. You put it into a dictionary because you can also compute natural gas charges. Most people don't care about that, but for wastewater treatment plants, that's important. So we have it in there. Again, so here I got the itemized cost, but in this case, because grid demand KW is an optimization variable, you can see I can actually, what I was returned is a dictionary of CVXPY variables. So I add together the energy and demand cost, again, ignoring the customer charge, and then just solve the problem. And I guess, again, I want to have you take away is if you come with your own optimization model, you can have 3 or 4 lines of code. You can compute an objective function for however complex of an electricity tariff you'd like. Another very important note is if you are computing this in an optimization problem, please compute the cost ex post. Meaning, you might be like, oh, why? You just compute the cost up here. Why compute it again? If you access the value of the objective directly, there may be some convex relaxations you apply. So it might not be the true electricity price. Like the value of, the objective may not be the true electricity price. So what you want to do is take the output load profile and recompute the electricity price with the NumPy load profile so that it's a static load, and you will get the actual electricity cost. So that's just a small nuance, but if someone has an idea of how you could avoid that, that'd be great. Unfortunately, like I mentioned, the charge tiers, there's just certain cases where I don't think you can just input the cost directly into it. CVXPY, so I think you have to sort of do this 2-step approach. Finally, you can also talk about emissions. Like I said, so the one motivation of this is you want to co-optimize costs and emissions. So the costing portion of this, you don't have to worry about so much. But for emissions, just know it's a similar, hopefully relatively straightforward thing where you get carbon intensity from a CSV file and then just put that into the objective function. I'll admit emissions are linear. It's not the same thing as demand charge and stuff. So it's a pretty simple problem. Like you probably don't even need this package if you know convex optimization to like add the emissions to the objective is straightforward. But this way you can do it all in one package and then just co-optimize the cost of carbon. And this is an example of the output. So like with the battery model, you'll see in blue was the historical load profile. In orange is the cost optimized demand. The first day of this is a weekend, which is why, so there's no weekend charges, which is why they only care about this peak period during the 10th of April. And then the green is the emissions optimized. And as you'd expect, overnight, when the emissions are highest, it goes down to 0. And when emissions are lowest in the middle of the day, because you're using solar energy, you have the highest consumption. So you can see like how you have the different results with the different signals. And then also sort of just validating what you expect. The costs are lowest for the cost optimized, in between for the co-optimized, and the lowest emissions is the co-optimized emissions profile. One thing to note, sort of that I alluded to before, the emissions go up in the cost optimized case. So that was like one of the initial things we're looking at. We would like the policymakers to rethink the incentives so that when you're cost optimizing, you're not raising your emissions. And we have some planned improvements, I guess. We want to do some stuff to improve the emissions calculation. It's a bit clunky. We want to actually, so right now you can compute the flexibility metrics. Like we have functions that let you, based on a historical load profile, give you the round trip efficiency or power capacity. We think it would be interesting to actually make those optimization variables, because then that would be more like an optimization for design of a flexible system of like, if I could pick any power capacity, what would be the best one? So that's a hopeful feature improvement we'd like to see and add in. And also, like Daly mentioned, we want to integrate this with some other work we've done on demand response. So you could have a package that's doing demand response and time use pricing optimization simultaneously. This is definitely very much in development. So if you have any questions, feature requests, you find any bugs, please let us know on the GitHub issues page. And just to like leave you with some potential use cases, you could do what we're already doing, which is optimal flexible operation. As I mentioned, you could size, so like not just operation, but do some design optimization, like how large my battery and my tank be. You could have tariff selection. So now there's a lot of times, especially in California, there's like 5 options. And a customer is like, well, I don't know which is the best one. You could optimize all 5 and tell you this is the one that gives you the minimal cost across all the suite of options, because you can look through this package. And I think maybe the most interesting one, which I haven't gotten to try yet, is actually informing the policy, where they can do hypothetical tariffs and see how a rational customer would respond to the price signal before it became a real policy. And that lets them to make sure, I would argue, you should align the cost and emission signals, for example. And that, thanks to my co-authors and maintainers, it's been a very collaborative effort with a lot of people in the WeFi lab and some help from the national labs as well.